Hi everyone, my name is Eros Cedeño. I am an undergraduate student at the Simón Bolívar University in Venezuela. I'm currently studying the 5th year of the computer energy degree, and today I come to present the research entitled An Evaluation of the Impact of End-to-End Core Optimization Strategy on Energy Consumption. I have carried out this investigation in collaboration with other students from my university and professors and professors from other universities that I mentioned here. And we are very pleased to present it to you today. So let's start by give us presentation structure. Okay, first of all, we have the proposal where we have the study design and the tools that we use and the general analytic consideration that we propose. Next, we have the result of the study. And at the end, we have the threats to validity, the conclusions, and the future works. Okay, so let's give us in context. Let's take in context. We have the software application actually intensively receive and transfer data by using relational database management systems. That is nowadays we have that a lot of applications rely on the database management system to transfer data to make interaction between the users that use the applications. But we have a problem that the relational database management systems are software components that could require a lot of hardware resource for a large database. So we know that resources are limited and expensive, so they must be used wisely. But here we have a problem. The developers are not aware of the resource impact they cause when building the software. For example, a few decades ago, we have seen that the application doesn't take care about the energy consumption for this application because the all digital system manage a really low amounts when we are talking about energy consumption. But nowadays the truth is different. We have an application that consume a lot of energy, and all these applications are running in the same device. So we have to take care about the consumption of the application by itself to reduce as much as possible the energy consumption they are taking from the device. Because of course the resources are limited and we have to administrate it in the best way as we can. Oh, okay, so the problem here is that the studies are traditionally interested in reducing execution time by implementing database optimization strategies such as index or compression. However, there are no studies dedicated to analyze the end-to-end, I mean server and client sides energy impact of this strategy. So our goal is to increase awareness about the end-to-end energy impact of database optimization strategy, so it can serve as a guideline for supporting developers to choose the strategy that are more energy friendly for them. So we set 2 research questions for this research. First, we have does the implementation of database optimization strategy affect the energy consumption of client-server application? And the second one is, does the addition of database optimization strategy affect the energy consumption of client and server application? Here in the first research question, we set it because we want to know if when we apply a database optimization strategy, does or does not make any effect on the energy consumption and the clients and in the server side for an application. And the second research question that we set here is because we want to know if when we combine different database optimization strategy, if that make any impact on the total energy consumption from the client and the server application. That is the term that we use here. We use the end-to-end term to refer exactly to the client and server side. And that is why we use the term end-to-end. Okay, let's continue. With the proposal, when we have the design of the study. So here we have the big picture of the study. We have for one side the client configuration, and for other side we have a server configuration. There are 2 parts that are independent and but work together to give us the result that we are expecting. So here we have the client configuration. The client configuration is a Java application that have a repertoire of 22 SQL queries. That is an implementation of the TPCH benchmark. The TPCH benchmark is a benchmark widely used for testing and taking the performance from the relational database management system. In this case, we use it with the PostgreSQL database system, but it can be used with other relational database systems. So we set the client configuration with a Java application and the 22 SQL queries from the TPCH benchmark. For the other side, the server side, we have 4 different configurations of 1 GB of dataset from the TPCH benchmark. First, we have the Postgres database without any kind of a strategy applying it. We have next the database system with compression, applying the compression in optimization. Next, we have the database system with index. Here we make indexation inside the database from some tables that require it. At the end, we have the database system with compression and index at the same time. Okay, the first one, the PostgreSQL database without a strategy, we set it because we want to have a point of reference of the performance from the database, for the total energy that the database consumes when we have not we have not any kind of optimization applying in it. So we can compare with this and we can study the different performance when we apply, for example, compression or index in the database management system. And at the end, we perform an evaluation with configuration with the compression and the index at the same time, because to respond the second research question, we want to know if the combination of all this make any impact in the total result of the energy consumption that we are studying. Okay, let's continue with the algorithm that we used for make this study. Okay. First of all, we require the list of optimization. As I mentioned, we have the base, the index, the compression, and the index and compression. All this optimization that we have is to compare each other. So next, we have the number of iteration. In this case, we set 30 iteration. We set this number of iteration because we need at least 16 iteration to can use the Wilkinson test. And so we want to mitigate out the possible fluctuation in the metrics that we are collecting for the energy consumption. Next, we have the list of queries that are the 22 queries from the TPCH benchmark. And what we are trying to ensure is to collect the metric for the analysis of energy consumption of the client and the server application. Okay, let's start analyzing the algorithm. First, we have that for every optimization in the list of optimization, we delete the database if it already exists. We do that because we want to recreate the database according to the configuration of this optimization in particular. Okay. Next, we have that for every query from the list of queries and for every iteration, we restart the service of database server and start monitoring tools. Once we have do that, we execute the query in the database server with the configuration and collect the metrics that are the execution time from the energy consumption from the client and from the server side. And at the end, we stop the monitoring tool and go to the next loop. So one thing that we want to highlight here is in the line number 7, we said that we want to start the monitoring tool, but what are those monitoring tools and what are they doing? Okay, for the client side, we choose to use the EulerGIS monitoring tools because the EulerGIS monitoring tools work fine when we are trying to analyze the energy consumption in a Java application. And of course, as I already mentioned, we have the Java application running in the client's side. So the Julia jigs worked fine when we are trying to analyze the energy from the client side. But here comes trouble. We want to take the energy consumption also from the server side, but the server side is not a Java application anymore. Here we have an application that is running at the operating system level. So we want to take it out from this and collect this metric to analyze it and make the report that we are hoping. So for this case, we developed a new, brand new, fast, and really minimalistic tool that we designed in this case was that we named it Juliet. So let's start talking about Juliet. Juliet is a minimalistic and energy-friendly tool that we developed in C++. Juliet is a tool that take the process name at the start of the process. He take the process name and the interval spread. Okay. In this case, we take this because we want to know which process we want to analyze, and the interval spread is how much frequently we have to go to the Linux interface to take the metrics and return to the total energy accumulated that we are taking. Okay. Juliet goes to the interface. In this case, we take care about 3 interfaces. We are looking at the system CPU metrics, we are looking at the process statistics, and the inter-air APL interface. That is really interesting that we are taking information from the inter-air APL interface, because the inter-air APL interface is an interface that the Intel processor provides at the software level, that we can take from this the metrics from the total energy consumed since the computer was started. So Juliet, every interval scrap, she goes to the interfaces, collect the metrics, and accumulate the total energy, and that goes to the next interval at the end of the process. And at the end of the analysis, we have the total energy of in microjoules. So let's study the results that we have. So just like a reminder that we have the first research question is, does the implementation of database optimization strategy affect the energy consumption of client and server application? And the second one, does the addition of database optimization strategy affect the energy consumption of client server application? So to answer this research question, we take as a sample the query number 22. Here we have the fourth configuration, and we have 2 groups from client and server. And from each group, we analyze the average of energy consumption, the relative standard deviation, and the difference from this configuration and the base optimization. So, for example, for the index optimization, we note a decrease of the 86% from the total energy consumed comparing with the base configuration. That is in the client side. In the server side, we note almost a 100% of difference, reduction of the total energy consumed. And at the same way, we have in the index compression of almost 19%, and in the server side, we have almost 100. But as you can see, the compression have a line here and have a line here, because when we apply the Wilkinson test, that gives us that there is not so significant difference to give a conclusion in this case. But for example, changing to the query number 16, we notice that the compression make a difference, for example, in this case of 45%, decreasing the total energy consumed. And in the server side, we have 33%. So that is a really good, really positive result, and that is what we are waiting for. But to make it in a compact way, we can say that, for example, for the research question number 1, the index strategy reduced between 1 to 100 joules for the client side energy consumption, while for the compression was from 1 to 20 joules. all this is in the client side, but for the server side, the index strategy reduced between 1 to 4,000 joules, whilst the compression reduced between 1 to 100 joules. So as you can see in conclusion, the index optimization make a better performance when we are trying to reduce the total energy consumed by the relational database system when we compare with the compression one. So to respond the second research question, for the index compression strategy, the reduction of the energy consumption was between 0.92 to 18.6% joules. For the client side, the server side was between 1 to 4,000 joules. So as you can see, those values are almost the same from that we obtain from only applying the index optimization, and when we combine the indexation and the compression together. So we can say that they are almost equivalent to use only the indexation and combining the index and compression strategy. Of course, this equivalence is when we're talking about the energy consumption. If we want to talk about the total space, for example, from the database, of course, we have a difference. But in this case, we are analyzing only the total energy consumption we can say that are equivalent in this case when we are analyzing the energy consumption. Okay. But we have some exception. For example, we have the query number 5, when we analyze the total energy consumed in the server side, we note an increasing of the total energy consumed. That also happened when we analyze the index compression, that we have an increasement of 16%. So that gives us to wonder what is so special in this query that make this different behavior. So we start analyzing this. For example, we have many joins, many group by. That could be the root cause from this behavior. We still don't know. This need a lot more a deeper study to take a complete conclusion, because at a simple GLAD we can say they're almost the same structure that the other queries that are running in the TPCH benchmark. So no, we don't see any special thing here. So we have to analyze this in a deeper way. Okay, so let's go to threat to validity, conclusion, and future works. We have the internal validity that Juliet could introduce a bias. So we have to analyze the Juliet in a separate way. We have to make tests over this tool to make sure that this tool gives us the correct metrics from the server side. We also have the construct validity that the same computer is used for running the client and the server side. Yeah, that is true. We make this in the same computer, but if we see in a deeper way, we can notice that the client and the server are running in process completely different, and we are analyzing at the process level. So the total amount of energy that we are collecting must be independent. Okay. We also have the external validity that the benchmarking is limited to 22 specific queries, or results cannot be generalized. Okay, that is true, but we also have to remind that these 22 queries is for a worldwide famous benchmark, that is the TPCH benchmark, and that give us guarantees that all these queries together are very representative sample for the real world scenario. Okay, so in conclusion, indexation tends to be more effective when data compression to reduce the energy consumed by the execution of the majority of the queries. In this case, the 16 of the 22 queries. The addition of indexation and compression does not lead to a better result comparing with the indexation. So more experiments are needed to understand the reason of why some queries do not follow this tendency. In this case, we have 3 of the 22 queries increase the energy consumption in some case, and 3 of the 22 queries do not show any effect when we apply the optimization in it. So yes, that give us future works. We have to run new experiment in a real history with software architecture. We have to run new experiments over the relational database management system, and with no SQL dataset. For example, we can take all these experiments and repeat it in a MongoDB database or a MySQL database management system. We also have to classify the query according to their complexity, for response time and size to run new experiments. We have to consider the trade-off of energy consumption of database optimization strategy with other resources. For example, the CPU, the input-output usage, and the total memory usage. And we also have to run new experiments to compare the Juliet performance with other tools like Scafandra or Power API, so that we can take certain about the Juliet tools collections are completely certain when we compare with the Scafandra or Power API, for example. So that is all. I want to thank you, and I want to thank the STIC AIM-Suite project and Energy for Climate Interdisciplinary Center who partially support all these projects. So thank you so much.